In this video, we're going to look at page 1 of the second part of Unit 5 notes, looking at graphs of rational functions. Now, we referred to rational functions that looked of this nature earlier on in the course. And we know that if I have the parent function of f of x equals 1 over x, that's going to end up graphing a hyperbola. We know this graph has some asymptotes, and we can make a little table of values to remember what the characteristic is. If I let this equal y. We know we can't plug 0 in. That caused us to have a vertical asymptote at x equals 0. That's a vertical asymptote. We also know that if we plug in the point 1, we'll get 1, and the function is odd, so that if we plug in negative 1, we'll get negative 1. And those are always very good points to graph anytime we're graphing a graph of y equals 1 over x. If we plug in points of 2, we'll get 1/2. If we plug in 1/2, we will get 2. And likewise, negative 1/2 would yield a y-coordinate of negative 2, and an input of negative 2 would give us negative 1/2. And so we have our parent function from earlier in the term. Now, we're going to do some variations of these graphs by making some changes take place. So if I look at question 1, we have describe how the graph of the function can be obtained by transforming the graph of the reciprocal function. Identify vertical, horizontal, and vertical asymptotes, and use limits to describe the end behavior. Determine the intercepts of the graph as well, or the function as well. Now we can see that the end behavior of this graph, as x approaches infinity, my graph keeps getting closer and closer to a y-coordinate of 0. That also happens, end behavior, if I let x go to negative infinity, I see the y-coordinate keeps getting closer to 0. And we're going to look at g of x and see how having these extra coefficients here, how that affects the graph. Now remember from our unit where we did transformations earlier in the term that these values of numbers have an effect, obviously, on the graph. And we know that this 3 is going to cause our graph to go left 3. We also know that this 2, a multiplier of 2, is going to make us have a vertical stretch by a factor of 2. So comparing this graph to g, we're going to have the transformations of left 3 and stretched by a factor of 2 take place vertically. Now, how does that graph look? Well, we know graphically that we now cannot put in negative 3 in place of x. That's going to cause our vertical asymptote to shift 3 units to the left. And we will now have a vertical asymptote at x equals negative 3, as opposed to up here we had a vertical asymptote at x equals 0. We had a horizontal asymptote up here where the graph's end behavior kept getting closer to 0, which caused y equals 0 to be our horizontal asymptote. Now, we're still going to have the same end behavior. This graph, comparing, again, the g of x to the f of x, it is slid 3 units to the left. However, it's stretched up by a factor of 2 vertically. Well, this graph for f is getting closer and closer to 0. All the values that correspond with g are basically twice as tall, but they're twice as tall as something that's close to 0. So this graph still has a horizontal asymptote at y equals 0. So we've talked about how the graph is transformed. We've identified the horizontal and vertical asymptotes. Now I'm going to graph the sketch of the graph. Now remember that the initial graph up here had over 1, up 1, had a point on the top branch of this graph. This graph, over 1, because of it being vertically stretched, will go over 1 and actually up twice as tall, so it will be up here. And likewise, usually when we go back 1 and down 1 on the parent function. Well, we're going to go back 1, and because of the vertical stretch, we would go down 2. And the graph will basically curve over this way. Now, I'm not showing where the intercept is here yet because I'm actually going to do a calculation for this. We do have to find what the intercepts are for our function. Now, in the f of x function, I didn't have any x-intercepts. It was impossible for this graph ever to cross the x-axis, nor did I have a y-intercept. There was no value I could plug in. I couldn't plug in 0 for x, so I couldn't get a y-intercept. So let's locate for this graph whether we're going to have any x-intercepts and y-intercepts. To be an x-intercept, remember, we want the y-coordinate to end up being 0. So what input is going to cause our output to be 0? So when will this graph be 2 over x plus 3? And we can see that that's never going to happen either. If I tried to algebraically solve this and multiply both sides by x plus 3, we can see what ends up happening. We get an issue. And I have 0 is equal to, these would reduce down 2. So x-intercept-wise, there's never going to be one. It's never going to have an x-intercept. So this graph is never going to cross this axis, and we kind of knew that up here based on it having a horizontal asymptote at y equals 0. Now y-intercept, on the other hand, I can actually see that my graph is going to have a y-intercept. As this branch comes down, it is going to cross this axis, and I want to have it accurately depicted on my graph. For the y-intercept, remember, we want to know when we enter 0 in, what do we get for y? That value will be our y-intercept. So what value of y, when I plug 0 in place of x, and I have my y-intercept occurring at 2/3. Now, if you can leave it as an ordered pair, technically, if we talk about something being a y-intercept, really 2/3 is the answer. Quite often, people will list them as an ordered pair too, just so that you don't get confused to think that it's the other intercept. But we'll graph that point. And notice that I can use some of the information from this graph that if I went over 3 and up 2/3, that I would actually go from this asymptote. If I go back 3 and down 2/3, I would also have a point. So I can get a very accurate picture of my graph actually depicted. Okay, so we know what these values meant as far as left and vertically shifting the graph and stretching it. And we also know that we have asymptotes and intercepts and can graph quite nicely. Now, number 2 looks quite different. And at first glance, you wouldn't think that there may be really necessarily a relationship between this graph and our f of x graph that was at the top, but there is. First thing we're going to do is we're going to do a little longhand division here. And I'm going to take this x minus 2, and I'm going to rewrite the h of x function so that it's going to look in a little bit different form. This division won't take very long to do. When I divide, I know that the x minus 2 goes into here 3 times. And I have a remainder here. -7 minus -6 gives me a range of -1. But I'm not going to put this as r equals -1 as we did when we divided some polynomials before. I'm going to actually rewrite this equation and take into account that when I divide x minus 2 into the 3x minus 7, I got 3, and then I have my remainder of -1, but I'm going to put it in the form of a fractional remainder so that I have an equivalent expression. This is algebraically equivalent to h of x. Now I may also want to write it like so, 3 plus -1 over x minus 2. Either one would be fine. So those are equivalent expressions to h of x. Now, when I have it written in that form, when I do the quotient, find the quotient of these two polynomials, or this rational function, I can actually then see the relationship between the graph of f of x that we had up above and this function better. I can see that there is a slide left. I can see that there has to be some type of a reflection, and I can see that there has to be some other type of a slide. So if I think about the nature of this, I know if I compare this to the parent function of f of x, that this graph has been shifted right, 2, and when we multiply a value by -1, we know that that's going to reflect over the x-axis. And then we know that this addition of 3 is actually going to make it go up 3. So if I had taken my graph from f of x at the top and literally could pick it up and make it move the way these transformation values would give me, I could regraph the graph by making it slide 2 to the right, reflect it over the x-axis, and then have it slide up 3. Now, we'll look at the graph, and I'll leave some room to graph the graph over here. But let's find a couple of other pieces of information as well. Let's look at what the x and y intercepts will be for this graph, and also what its asymptotes will be, because this function will have asymptotes because it's a transformed parent function from the 1 over x graph, and because of that shifting, we're going to get some x and y intercepts as well. All right, so let's find the x-intercepts first. Intercepts or sept. For the x-intercept, I want to find where it's going to cross this axis, and this axis has the y-coordinate 0. So again, I'm looking for what value causes the y-coordinate to be 0. Now, make your work easy. You have a couple different places you can look. This graph and this function and either of these two functions are all the same thing. They're algebraically equivalent. Take the form that's easiest to work with. If I want to solve and find what value do I plug in for x to make the y-coordinate turn to 0, any of these can be used. I'm going to use the original actually here. When I multiply both sides by x minus 2, I'll end up getting 0 is equal to 3x minus 7. Adding 7 to both sides and then dividing by 3, be careful about your algebra, I'll end up getting 7/3. So I know that I have an x-intercept at 7/3, or that point on that graph will look like the point 7/3, or 2 1/3, and 0. I'm going to actually go over here and plot it now. So I know I have a point at 2 1/3 and 0. Now on the other hand, let's find our y-intercept. Our y-intercept is going to occur along the y-axis, and that's going to be when x is 0. And once again, use the form that's going to be the easiest to use. And so when I have this original, if I plug 0 in place of x and find out what y is going to equal, put 0, I find out that it's going to take place at 7/2. So there's my y-intercept. That's the point that it will be contained for the y-intercept, and that's at 3 1/2. The y-intercept is 3 1/2. So I plotted that point as well. Okay, now I know when I graph my graph, I have to have those points contained in the graph. Now let's get to our asymptotes. For the asymptotes, it's very nice to look at the divided form. So first of all, we know that vertically, I used to have a vertical asymptote at x equals 0. Because my graph has shifted 2 units to the right, my vertical asymptote has now shifted over to x equals 2. Make sure you write the equation of the line. Don't just put down 2 for an asymptote. You will get all the points taken off for that. It needs to be an equation. I will dot that equation in, and show that the graph is going to approach that. Now likewise, we know that horizontal asymptote for the parent function was at y equals 0. And because my graph has been shifted up 3 units, my horizontal asymptote will be shifted up to y equals 3. Now, I don't have any vertically stretching taking place on this graph. There is no multiplier up here other than the -1, which is causing it to reflect. And notice how these intercepts are set up. We knew that the graph was going to go right 2. Notice the vertical asymptote shifting right. The horizontal shifted up 3. We know that the graph reflected over the x-axis because of this negative coefficient up here in the top. And that caused, instead of having the branch be up here, it's causing it to be down into this little bit lower quadrant, if you want to call it, of the graph. It would still take place over 1, but down 1 now because of that reflection. And likewise, the same thing would happen over here, over 1 and up 1. Normally we had a branch over here and down in this region, but we aren't going to have that this time because of that negative in front of that 1 up in the numerator of that fractional part. So I'm going to sketch my graph. Now if you want to try another point to make sure that your information doesn't have any type of a mistake, then you can go back to the original form of the equation and say, try to plug in some value like a -2 or a 1 and verify that those points will work on your graph. But you need to be able to look at a rational function, explain what is happening as far as the transformation. The easiest way to do that is to start out doing the longhand division like I showed, to come up with a new expression that will re-emphasize how the graph is shifting. It's very hard to look at this original function and tell that the graph will have a reflection over the x-axis. Now we can see that the vertical axis or the vertical asymptote is going to be shifted, but it's a little difficult to tell that you're going to have this reflection take place unless we have it in this revamped form. Okay, so that's always the thing to start. Anytime you have a rational function, your asymptotes will be easier to see and the reflections will be easier to see if you do the division to begin with.